All right, we're back for discussion 4-1, hybridization and allotropes of carbon. All right, so we talked about Lewis structures and drawing Lewis structures in IB Chem 1 and in the pre-unit 4 podcast. Sometimes there's more than one possible Lewis structure for a compound that will, they all obey the octet rule. So we need some kind of way to say which structure is the most correct. To do that, we use something called formal charge. And the formal charge is just the charge that is assigned to an atom in a particular molecule. And we can calculate formal charge by taking the number of valence electrons in the atom, subtracting the number of bonds attached to it, and subtracting the number of non-bonding electrons surrounding it. And we can also calculate formal charge for molecules. To do that, we simply calculate all the formal charges for all the individual atoms and subtract the maximum formal charge, from the minimum formal charge. And the idea here is to get the overall formal charge to be as close to zero as possible. All right, so a good example here is sulfur dioxide. Sulfur dioxide has two possible Lewis structures, one with a central sulfur atom double bonded to two oxygens, and the other with the central sulfur atom double bonded to one oxygen and single bonded to the other. So to calculate the formal charge for each molecule, we have to go through and calculate the formal charges for each atom in the molecule. So the first thing I'll do is calculate the formal charge of the oxygen on the left. So the number of valence electrons in oxygen, which is 6, minus the number of bonds connected to that oxygen, which is 2, a double bond, minus 4, which is the number of non-bonding electrons around that oxygen. And we get a formal charge of 0. And we do the same thing for the sulfur atom. We also get a formal charge of 0. When we do the same thing for the second oxygen, we also get a formal charge of 0. So to find the overall formal charge in the molecule, take the max minus the min, which is 0 minus 0, which equals 0. So it's already looking pretty good for that Lewis structure. So now let's do the same thing for the other structure. The formal charge for the first oxygen, which is in the same situation bonding-wise as the oxygen in this Lewis structure, so its formal charge is 0. The formal charge for sulfur in this case is 1, and the formal charge for the second oxygen is minus 1. So to calculate the formal charge for this molecule, again, we do the max minus the min. The max is 1 minus the min, which is minus 1, which equals 2. So this Lewis structure shows a formal charge closer to 0, so it, is the preferred structure. All right, so resonance and electron delocalization. So electrons that are involved in double and triple bonds are actually free to move around between equivalent bonds. In other words, they are delocalized. Now this improves stability in the molecule because the formal charges on all the atoms are spread out and shared throughout the molecule. And it also will equalize the bond lengths and strengths between equivalent bonds. And I'll show you what I mean by that in the next example. So when you have to draw resonance structures, you have to draw all of the possible structures showing the double and triple bonds in all the potential locations they could be. So for the nitrate ion, we see it has 3 resonance structures. Now each nitrate ion will have 1 nitrogen-oxygen double bond and 2 nitrogen-oxygen single bonds. Please note for the polyatomic ions, when we do Lewis structures, we put them in brackets and show the charge outside the brackets. That just shows that this minus 1 charge applies to the entire ion. Now, when we see the 3 Lewis structures, you see that the nitrogen-oxygen double bond could be up here on top, it could be over here on the left, or it could be over here on the right. But in reality, those double bond electrons are actually delocalized and can travel wherever they want in the molecule. That means that we would expect to see, based on this one structure, this nitrogen-oxygen single bond to be longer and weaker than the nitrogen-oxygen double bond. But what we actually see when looking at the nitrate ion is all the bond lengths and strengths between those nitrogen-oxygen bonds are all equivalent. So take a moment, pause the video, and try to do the same thing with the carbonate ion by drawing all the potential Lewis structures. All right, go ahead. All right, so just like nitrate, the carbonate ion has 3 possible Lewis structures, one with a double bond down here on the left, one with a double bond here on the right, and one with a double, or top, and one with a double bond here on the right. All right, so physical evidence for the structure of benzene. So benzene looks a little bit something like this. Has the molecular formula C6H6. And what we see here is that benzene is a hexagonal ring of carbon atoms with alternating carbon-carbon single and double bonds. You also see it written in skeletal structure, the skeletal structural formula like this, where it's just the hexagonal ring showing the alternating double and single bonds, or you'll see it as a hexagonal ring with a circle in the middle. And the key to the structure is resonance. Because if benzene were actually a straight chain triene, first of all, it wouldn't have the structure or the molecular formula C6H6, but what we'd also expect to see is slightly longer longer and weaker carbon-carbon single bonds, and slightly stronger and shorter carbon-carbon double bonds. But what we actually see is that in benzene, all the bond lengths and strengths are equivalent, right? And again, without that resonance, we'd expect to see longer, weaker carbon-carbon single and shorter, stronger carbon-carbon double. All right, so how are bonds formed? Well, all covalent bonds are formed by the overlap of atomic orbitals. Now in this class, we only have to concern ourselves with the overlap of s and p atomic orbitals. And there are two types of overlap. The first is head-on or end-to-end overlap, which is also known as axial overlap, or sideways overlap, which actually is overlap that occurs above and below the plane of the bond. So let's look at these one by one. So axial overlap looks a little bit like so. You can have different combinations of orbitals combining, but the common thread is that they're all combining in a head-to-head arrangement. So we can have two s orbitals combine, and that region of overlap is where the bonding electrons will live, that shared pair of electrons. And you could have two p orbitals combining. Now they have to turn 90 degrees to achieve the head-on overlap, or you could also have an s and p orbitals overlapping. Now, all three of these examples are examples of sigma bond formation. Now, head-to-head overlap will... All right, and then the sideways overlap occurs here above and below the plane of a sigma bond. Okay, and those bonds that are formed above and below the plane are known as pi bonds. All right, so summing up, sigma bonds are formed by the head-on or end-to-end overlap of atomic orbitals, and pi bonds are formed from the sideways overlap of atomic orbitals. Okay, so sigma bonds are always the first bond to form, and that's actually really, really important, because if you have a double bond between two atoms, that double bond will consist of one sigma bond and one pi bond, because the sigma bond always forms first. If you have a triple covalent bond, then the bond will consist of one sigma bond and two pi bonds. All right, so how do pi bonds help us understand resonance? Well, this is going to be summing up a lot of what we talked about. So because pi bonds are caused by that sideways overlap, they're not as strong as sigma bonds. So the electrons involved in those bonds are able to move around. In other words, they become delocalized. And the example is the nitrate ion, where those delocalized electrons are allowed to move wherever they want. Again, this increases the stability of the molecules by spreading the formal charge out amongst the whole molecule. All right, so hybrid orbitals. So actually when you mix s and p orbitals, you'll actually get what are known as hybrid orbitals. And these are basically just formed by the blending of the different orbitals. Now, these hybrid orbitals are actually what give rise to the shapes that we see in molecules. So ask yourself this question. Based on the geometry of the p orbitals, considering the fact that they are aligned to the x, y, and z plane, would it be possible to have 109.5 degree bond angles? So stop and think about that for a moment, pause the video, and we'll come back to it. All right, so in reality, if you looked at just bonding that occurred between one p sublevel, you'd actually expect the bond angles to all be 90 degrees, since the orbitals are all aligned to the Cartesian plane. But when you take those three p orbitals and combine them, mesh them together with an s orbital, you get what is known as an sp3 hybrid orbital. And the sp3 hybrid orbital looks like this, and it is actually what gives rise to the tetrahedral geometry. And so when you combine an s orbital with two p orbitals, they'll hybridize to form what's known as an sp2 hybrid orbital, and that gives rise to the trigonal planar geometry. Finally, if you take an s orbital and combine it with a single p orbital, you'll get what's known as an sp hybrid orbital, and the sp hybrid orbital will give rise to that linear geometry that we see. All right, so it's really easy to assign hybrid orbitals, or to determine what kind of hybridization exists around a certain atom. And to do that, we just look at the number of electron domains around that particular atom. So if there's 2 electron domains, that means that you have sp hybridization. If there's 3 domains, it means you have sp2 hybridization. And if there are 4 electron domains, it means that you have sp3 hybridization. So whenever you're asked to determine the hybridization around a particular molecule, a good step is to actually draw the molecule so that you can determine the number of electron domains around that atom. So methane looks like so. We see that methane has 4 electron domains around the carbon, so the hybridization around that carbon atom is sp3. CH2O, this is methanol, which has a structure like so. We see that the carbon atom has 3 electron domains surrounding it, so its hybridization will be sp2. Ethine has a carbon-carbon triple bond, so it has 2 central atoms here, right? Both carbon atoms, and since both carbon atoms have 2 electron domains around them, we'll show sp2 or sp hybridization, excuse me. I don't know why I didn't edit that before. I did a lot of copying and pasting without any editing, apparently. Okay, and then finally for ethene, there's also 2 carbon atoms. We see that each carbon atom has 3 electron domains, so each one will have sp2 hybridization. All right, so take a moment to practice this. Now what I want you to do is pause the video and draw the structure for each molecule. And then for each molecule, for each central atom, state the geometry and the hybridization around each central atom. So take a minute, pause the video, and do that. And then we'll come back and go over each one. All right, so when we draw ammonia, we see that it is nitrogen single bonded to 3 hydrogens with a lone pair of electrons on the nitrogen. That means the geometry around that nitrogen atom will be trigonal pyramidal, right? And the hybridization, because there's 4 electron domains, will be sp3. Now for carbon tetrachloride, we have a central carbon covalently bonded to 4 chlorine atoms, so the shape is tetrahedral. And there'll also be sp3 hybridization around that carbon because there's 4 electron domains. And for propyne, we see 3 central atoms, all carbons, and there's going to be different hybridization around, well, each one. So the first carbon here will have 3 hydrogens coming off from it, and it's also single bonded to a carbon. So that's 4 electron domains, so it will have sp3 hybridization. Both of these other 2 carbons will each have 2 electron domains around them, so they are both sp hybridized. Excuse me. And then finally, propan-1-ol. Now, propan-1-ol has 4 central atoms, 3 carbons, and 1 oxygen. So if we look at them one by one, we see these 3 carbons will all have a tetrahedral geometry. And each one has 4 electron domains, so each one will have sp3 hybridization. Now this oxygen atom here has 2 bonds and 2 lone pairs, which means that it is in the bent shape. But because it has 4 electron domains, it will also be sp3 hybridized. I don't know why I have so much trouble with that word. All right, so allotropes of carbon. So covalent bonding truly is not always the same, even for a substance that is in the same in terms of its composition. So a great example of that is carbon, right? And an allotrope is basically just different physical forms of the same element. So what you got to do is look at all the different allotropes of carbon and explain a few things about them. So carbon has 4 allotropes: diamond, graphite, graphene, and the C60 Buckminster fullerene, which is really fun to say. All right, so you've got to compare the structure, strength, and conductivity of each of those allotropes. Now I'm going to really quickly go through each one because essentially you really just need to read this material and kind of know it. All right, so in diamond, you have what's known as covalent network bonding. So we have covalent, what that means is we have covalent bonding, but it's not individual molecules that we see. Right? We see basically atoms bonded to each other on until essentially infinity. Right? So in a diamond, what we have is a covalent network bonding where each carbon is bonded to 4 other carbon atoms, which would give us sp3 hybridization. Now, diamond is very, very strong and very, very hard, as you know, and that is due to the fact that there are no delocalized electrons in that species. And the fact that there are no delocalized electrons means that it is not conductive. Now, graphite is also network bonding, but graphite is slightly different. It's layers of hexagonal rings where each carbon atom is bonded to 3 other carbon atoms. So there's sp2 hybridization. So those hexagonal rings are literally stacked on top of each other, one after another. Now, pencils are made out of graphite. And when you're writing with your pencil, what you're actually doing is leaving layers of graphite on the ground, or on the paper, excuse me. Now, each layer itself is very, very strong, but because they're held together by those weak intermolecular forces, it's really, really easy to pull them off. And because there are delocalized electrons, graphite is actually very, very conductive. We've actually used graphite in IB Chem 1 as electrodes. And then there's graphene. Graphene is basically just one sheet of graphite. Right? And it's literally just one atom thick. Now again, just like graphite, it's a series of hexagonal rings with each carbon atom bonded to 3 other carbons. Right? And when we take graphene and roll it up, we produce what are known as carbon nanotubes, which are incredibly strong and flexible, and they're very, very, very conductive because of those delocalized electrons. Finally, the C60 Buckminster fullerene is the only one of the carbon allotropes that has a molecular structure. In other words, it's made up of molecules as opposed to being a network or a giant structure. Now, in the Buckminster fullerene, you get 20 hexagons and 12 pentagons. So the final product looks just like a soccer ball. Now, in the C60, each carbon atom is bonded to 3 others, so you get sp2 hybridization. Now, within the molecule, the carbon-carbon bonds are really, really strong, but there's weak London forces between the molecules, so it's not really hard to separate them. Now, the C60 is not conductive, all right? So electrons are able to move within each molecule, but they don't go from one molecule to another, so it is not conductive. And finally, silicon dioxide. Now, in silicon dioxide, you really do get a special type of bonding. Now, this is another network structure, just like diamond, but it's slightly different because silicon is non-metallic. It has some ionic character and some molecular character when it bonds with oxygen. Right? So what we get is, what we get is quartz. Silicon dioxide is quartz. And in that structure, you'll see that each silicon is bonded to 4 oxygen atoms, and each oxygen atom is bonded to 2 silicon atoms. Now, you do need to know that, and it's actually pretty easy to remember because silicon, being right below carbon in the periodic table, has 4 unpaired electrons ready for bonding, and oxygen has 2 unpaired electrons, and so it tends to make 2 bonds. All right, now the structure is known as a giant covalent structure or a macromolecular structure. The IB will accept either. But the essential idea is that you know how the bonding works in silicon dioxide and the fact that it's macromolecular or giant covalent network bonding. And finally, coordinate covalent bonding. We talked a little bit about coordinate bonding in topic 2.2. But we're just going to bring it back up here. So coordinate bonding occurs when one species involved in a bond will donate both of the bonding electrons. A great example of this is carbon monoxide. Now, since carbon has 4 unpaired electrons around it and oxygen only has 2, when carbon monoxide, in carbon monoxide we have that triple bond. And because of the structure of those atoms, oxygen can only provide 2 of the 6 bonding electrons. That means that the other 2 need to come from carbon. And this bond right here, where both of the bonding electrons come from carbon, is the coordinate bond. Finally, the ammonium ion. And the ammonium ion is formed when a hydrogen ion attaches to ammonia. Now, a hydrogen atom, you recall, has only one electron. So when you have a hydrogen ion, basically what you just have is a proton floating around with no electrons to donate. So when the hydrogen ion reacts with the ammonium ion, it sticks to the lone pairs on the nitrogen to form that coordinate bond. So the ammonium ion has 3 standard covalent bonds and 1 coordinate bond. All right, and that's it for discussion 4-1. If you have any questions, please bring them to class. I'd be happy to answer them, and have a great one.